Hello. This tutorial is an attempt to explain how skinning works. Specifically, how the ViewScene example code computes the necessary transformations to deform a mesh. This is intended to supplement the ViewScene example code and the FBX Programmer's Guide, not as a standalone tutorial. I will start with a few quick remarks about matrix transformations in FBX. Then I will derive the cluster deformation formulas used in the ViewScene example code. Note I will derive these formulas step by step by starting with simplified cases and then modifying them to handle more complex situations. The final formulas will match those found in the compute cluster deformation function in the drawScene.cxx source file of the ViewScene example code. Lastly, I will say a few words about how cluster deformations are actually carried out. For this, I will assume the cluster mode is E-additive. The full code to carry this out can be found in the compute linear deformation function, also in drawScene.cxx. Before I begin, I should point out that I often use the word vertices when I refer to the points on a mesh. Keep in mind the correct term in FBX is control points. I also will use the words bone node and link node interchangeably, but the correct FBX term is link node.
Okay, first I just wanted to say a few words about matrices and transformations in FBX. In FBX, a vector that is transformed by a matrix is right multiplied by the matrix, which just means that the vector appears on the right in the multiplication process. This is important to keep in mind because when you string together multiple transformations, which side the vector hits it determines the sequence in which the transformations occur. In this case, the transformations will be first by C, then B, then A. Consider the two transformations shown. Transformation A involves a translation and a rotation, and transformation B involves only a vertical translation in the y direction. Now very often we want to modify one transformation, such as transformation A, by another transformation, such as transformation B. We can do this by either left multiplying or right multiplying A by B, and each one has a geometric interpretation. Suppose we multiply A on the left by B. Keep in mind that B is a vertical translation in the y direction. In this case, the transformation A gets translated vertically in the y direction, with the y being relative to the origin. Now suppose we multiply A on the right by B. In this case, the translation still happens in the y direction, but the y is relative to A's transformation, or A's coordinate system. In short, left multiplication by B means the translation happens globally, or relative to the origin. Right multiplication by B means the translation happens locally, or relative to A's transformation. Keep in mind, this is all because FBX uses right multiplication of vectors by the transformation. One last remark I'd like to make on this topic. Suppose we have a mesh node with a transformation A. The coordinates of the vertices on the mesh are measured in A's coordinate system. To get the coordinates in global space, or relative to the origin, we multiply the mesh vertices by A. We can do this process in reverse. If we are given the mesh coordinates in global space, we multiply them by A inverse to obtain the mesh coordinates in the mesh's local space.
Okay, so now I'm going to talk about skinning. Suppose we have a mesh node with a mesh, shown in dark green, and a bone node, or link node as FBX calls it, with global transformation B initial. At the present point in time, the link has moved from its initial or bind pose position to a new location B final. The initial mesh needs to be deformed so that it shifts and rotates in the same manner as the bone to obtain the current mesh position, shown in light green. Let's assume for now that the vertices of the mesh are given in global coordinates. We want to know the global transformation that shifted the bone from its initial to its current location, and then apply the same transformation to the mesh. This is the matrix shift global that moves from initial to final in global space, and so satisfies this equation, which can easily be solved. So the mesh needs to be shifted by B final times B initial inverse. There are two more small pieces needed to make the deformation suitable. We assumed the mesh coordinates were in global space, but they are actually given in mesh space. So first, we need to convert the mesh vertices to global space by multiplying the global shift on the right by the mesh node's transformation M. Second, in the view scene example code, the mesh is deformed and rendered in mesh space. That is, the current OpenGL transformation matrix will be the mesh node's transformation. Therefore, we need to measure the deformation in mesh space. We have the deformation in global space, so the last step is to multiply on the left by M inverse to move back into local mesh space. This formula works fine for the situation shown, but there is a potential problem for other situations. The problem is that sometimes we want to deform the mesh due to relative motion between nodes, rather than global motion. Consider the model shown here. Imagine what would happen if link A were to shift slightly to the right. This would shift the mesh a little to the right. But notice that link B, being a child of link A, will also move to the right by the same distance. But since no relative motion would occur between links A and B, we might not want link B to cause any further deformation. If that is the case, when we compute the shift of link B globally, as we did before, we need to cancel out the global motion of link A, so we are left with the amount that link B moved relative to link A. By similar reasoning as before, the global shift from A final back to A initial is given by A initial times A final inverse. This is the amount we need to cancel out from B. So the corrected transformation is M inverse times A initial times A final inverse times B final times B initial inverse times M. Note, however, that B's motion could have been measured relative to any other node, not just A. For example, you might prefer to measure B's motion relative to the mesh node M for a different effect. To allow for this, FBX keeps track of which node a given link's motion is measured relative to. This node is called the associate model of the link. In this particular case, link A is the associate model of link B. If you let A stand for associate model in this formula, the logic still holds and the formula is more general. The deformation formula is almost perfect, but there is one more little detail to worry about. The problem is, the mesh node might move, but fortunately this doesn't complicate things that much. The view scene example code splits the overall mesh motion into two independent parts: the mesh deformation, in which the shape of the mesh changes relative to the mesh node, and the mesh node's transformation, in which the position and orientation of the mesh's coordinate system changes globally. Here, for example, the mesh has been deformed vertically, but transformed to the right. First, let's compute the deformation. The formula we use for deformation will still work fine, but do we use m initial or m final in place of m? Since we are shifting from bind pose to the current pose, we want to start off with m initial. At the end, we transform by m initial inverse to move back into local mesh space. The mesh deformation has now been calculated, but the mesh node transformation, the rightward shift, has not occurred. The rightward shift is taken care of during rendering. In the ViewScene example code, all meshes are rendered relative to their current node location. So the mesh node will be rendered relative to m final with the appropriate deformation. So our deformation formula is complete. This is the deformation with respect to a link B with associate model A to be applied to a mesh M. This is the exact formula used by the ViewScene example code in the compute cluster deformation function in the drawScene.cxx source file. But a fair question to ask is, what if no associate model is specified? That is, what if we are not told how to measure the relative motion of bones? The answer is, we assume the point of reference is the mesh node, which is to say, we assume A equals M. Observe how our deformation formula simplifies due to a cancellation on the left. And now we get the second formula used in the compute cluster deformation function. The top formula is used only if an associate model is present and the cluster mode is E additive. Otherwise, the bottom formula will be used. Note that in the code, they refer to the above transformations as shown. M is called the reference, B is the cluster, and A is of course the associate. Here's just a quick look at how these deformations are carried out. Here is a model originally made by Jiang Xu that uses rigid binding in E-additive cluster mode. If you go through the example code, you'll see that each mesh has a set of skin deformers, and each skin deformer has a set of clusters. Each cluster refers to a link node and a set of weights specifying which vertices are influenced by the link, and by how much. Clusters are responsible for all mesh deformations. Here, I modified the ViewScene code so I can look at different clusters. The bright yellow dots are the vertices influenced by the cluster. The green coordinate system is the link of the cluster, and the blue coordinate system is its associate model. Each of these clusters add their own deformations to the mesh one by one. The last thing I'll discuss is how we add deformations together. How clusters are added together just uses some simple matrix algebra. Each cluster will produce a matrix describing its influence, or its contribution to the deformation. Here's some pseudocode which roughly reflects the code in the viewscene.cxx example code. The idea is that if the weight were, say, 0.25, we would use 25% of the new deformation appended to the old, and 75% of just the old deformation. If you know your matrix algebra, you can simplify the update formula as shown down here. You can now use the matrix scale and matrix add to diagonal functions as shortcuts. Alright, well, I hope this tutorial was helpful to you. Questions, corrections, comments, or criticisms are welcome, so please give me some feedback on the message boards. Thanks.